All right, I think everyone is in already. Just as a reminder, if you would like to join us through Zoom, that is also okay. So the first question that was brought up was this from the end of section questions. It says the age of very old rocks can be found from uranium dating. Uranium is suitable because of the very long half-life of 4.5 times 10 to the 9th years. The final stable product in the decay series of uranium-238 is lead-206. Find the age of rocks that are measured to have a ratio of lead to uranium atoms of 0.8. You must assume that no lead was present in the rocks other than that due to uranium decaying. Right. So first of all, what we have to find out is that this ratio is not the final amount of the sample, right? This ratio represents the ratio of lead divided by the number of the uranium atoms, right? In this case, the ratio is going to be 0.8, so it's 1 and 5. Oh, sorry, 4 and 5, right? So this, the lead divided by uranium has to be equal to 0.8, right? Which means it's a 4 to 5 ratio approximately, right? So what does this mean? This also means that if the final number of uranium atoms can be said to be equal to 5, the initial number would have been around 9, right? 4 of these turn into lead, which is a 4, and then the remaining is the uranium, right? Now here, there's two ways to do this. There's a long way and there's an easy way. I'll tell you the easy way. And the easy way is not to use the E-based, natural log-based equation. We can just use the normal equation, which is n equals initial number times 1/2 t divided by the half-life, right? We don't need any of the other variables. You just need to find the time, right? To do this, let's divide both sides by the initial number. We take any log, right, of both sides. It could be the natural log, it could be just any log function base 10. It doesn't really matter. You get log of n divided by n0 is equal to t divided by the half-life times the log of 1/2, right? Up until this point forward is just an algebraic equation you can solve, because we know that this part is going to be 5 divided by 9. So this is a log of 5/9 equal to t divided by half-life times the log of 1/2, right? You could have simplified before as well. It wouldn't have mattered. Just 1 second. And we'll find that the half-life, sorry, not the half-life is looking for, we're looking for the time is equal to log of 5/9 divided by the log of 1/2 multiplied by the half-life, which we know. The actual calculation I'll leave to you. You can use your calculators. You should get an answer that is approximately 3.8 times 10 to the 9th years. The second method is quite a bit longer. I will post the longer method in OneNote after class. For now, we'll just move on to question 25. And question 25 says, a particle mass m and charge E is directed from very far away towards a massive object of charge ZE with a velocity of v, as shown in the diagram. This is basically the Rutherford experiment, correct? The distance of closest approach is d. Sketch on the same axis a graph to show the variation with separation. So you want to find the kinetic energy with this separation. And you want to find the particle's electric potential energy with the separation. So one thing a lot of students might be confused with this is that it's a two-dimensional graph with distance, and you have to somehow add this kinetic energy, potential energy as well, right? And that is not true. When you draw this graph, you only have this distance d on one side and all the rest energies on the other axis. Let me show you what this would look like. Let me zoom out from here, so I have enough space to show you. And the answer to this question would be this graph here. Again, x-axis, the distance, d. We just changed d to r. The vertical axis is the energy, right? And first, it says the particle's kinetic energy, right? Of course, the kinetic energy of this particle, right, decreases as it gets closer, right? Can you see that? This is the distance d. As it gets closer and closer, it decreases. And as it gets closer and closer, the potential energy increases. Right? This is not exactly the shape it should have, right? The exact shape it should actually have is, we know the equation for potential energy for two charges, right? And the potential energy equation EP should have been Coulomb's constant, charge 1, charge 2 divided by R, right? This means it should go more in the shape like so. So I'll erase the other one that is not correct. Actually, let me erase the other one first. Go kind of like this, right? Inverse function. Okay, if there is no further questions about this, if you would like the equation for the kinetic energy, well, the kinetic energy is decreasing, but the kinetic energy has to have been a certain maximum, right? So this kinetic energy doesn't actually look like this either. Has to go in a curve such like that, because it has a maximum kinetic energy, right, when it's really far away from this atom, right? So it stabilizes at a certain asymptote. So there's a max kinetic energy when it's really far away. There is a limit to this kinetic energy, right? So how does it vary? Well, as it gets closer, you just have to take away the potential energy, right? So it has this maximum kinetic energy, or the initial kinetic energy that had before it came anywhere close to this atom. And then from here, you're going to subtract the K, Q1, Q2 over R, right? So it goes down like so. And when it reaches the minimum distance, right, the kinetic energy is actually 0. It cannot get any closer. This would be the case where it's head-on, right? Where it goes head-on like this and goes back. In any other case where it doesn't go head-on and it kind of deflects, it does have a minimum here, right? More or less. Right. So, for today, if there's no further questions, we will move on to the review of Chapter 12. And we review it by doing, of course, questions related to Chapter 12.